A very good morning, everyone. Today, I'm excited to present our project, which focuses on sound measurement and analysis using advanced tools like DesiLab software and portable microphones. Before I would like to continue present, I would like to introduce myself. My name is Kuan Raj Analaki Manimaran, student ID MA22094. So let's back to the presentations, where the primary aim of this study was to evaluate sound intensity measure in decibels, and distinguish useful sound signals from background noises. This project highlights the significance of visual instrumentations system for real-time data acquisition and analysis, ensuring accuracy and reliability in acoustic measurements. These systems play a critical role in applications such as industrial noise control, machinery, condition monitoring, and research-driven insight. So our main objective was to explore the efficiency of visual instrumentations systems and assess the reliability of portable microphones for real-time sound measurement. Additionally, we had several secondary objectives. These included analyzing and differentiating useful sound signals from noise, assessing the sensitivity and reliability of MEMS microphones, especially at high frequencies, and validating our result by comparing them with data collected from mobile sound meter applications. Finally, we utilize advanced data processing techniques including FFT, which is fast Fourier transform, and time domain visualization to ensure a comprehensive and accurate analysis of acoustic signals. That's all from me. Thank you so much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Malik. My metric number is MA22090. So today I will be discussing the theoretical background of vibration and acoustic measurement and its important in various industries. Vibration and acoustic measurement are critical in identifying structural and mechanical issues. This measurement rely on capturing sound wave and pressure changes caused by object vibration. Microphones are commonly used as a transducer in this process. They work by converting the physical displacement of diaphragm into electrical signal that represent the intensity and frequency of vibration. Once captured, these signals are processed to provide fundamental data such as amplitude and frequency. This information is vital for diagnosing problem, assessing structural integrity, and controlling noise level. This approach is heavily utilized in industry like automotive and aerospace, where ensuring safety and compliance with quality standard is paramount. Understanding the vibration characteristic help engineers design safer and more efficient product while addressing potential risks before they occur. Moving on to the practical application of vibration and acoustic measurement, they are widely used across various fields. For example, number one, structural health monitoring. This involved by detecting and monitoring the structural integrity of building, bridge, and other infrastructure. For example, accelerometer can sense crack or weaknesses in the bridge, providing early warning to prevent catastrophic failure. The second one is environmental noise monitoring. Here, the focus is on assessing and controlling noise pollution in line with regulatory requirement. For example, microphone can be deployed at construction site to monitor noise level and ensure they are within permissible limit. The third one is machinery condition monitoring. By analyzing vibration pattern, we can predict maintenance needs and prevent equipment failure. A typical example is detecting abnormal vibration in industrial equipment to identify potential issues early. The fourth one is automotive testing. Testing involves assessing the noise, vibration, and harshness, commonly known as NVH of vehicle. For example, engineers measure vibration in car engine and cabin to reduce noise and improve passenger comfort. This application demonstrates the versatility and importance of vibration and acoustic measurement in ensuring safety, efficiency, and compliance across various industries. That's all.
Hi, I'm Rubin Ranat, ID number MA22028, and I will be presenting on the apparatus and experiment setup. So the device that we have chosen is electric kettle, and the apparatus we have is PC with DesiLab, electric kettle, portable microphone, and sound meter. So the diagram shown here is our setup. Next is our Daisy Lab layout. So this is how we input our Daisy Lab into the software. So the top layer is the time domain layout, and the bottom layer is the frequency domain layout. So these are the options and parameters that we need to set for each input. So this is for measurement setup and analog input. Next is YT chart and digital meter. Next is interpreter to gain the formula, write data, data window, FFT, a digital meter. This is to obtain our decibel value, and YT chart, FD. And last but not least, this is the final output that we got. The VRMS domain layout flow process, it displays the voltage, um, and then the decibel domain layout flow, it calculates the sound intensity, providing the sound level for further analysis later on. So that's all from me. Thank you.
Assalamualaikum. My name is Muhammad Amar bin Shamsul Bahrain. My metric ID number is MA22007. So, for my part, I will talk about the result and discussion. So, in this part, I will talk about time domain plot, frequency domain plot, formula interpretation, and key findings. So, in this slide presents the time domains analysis of the acoustic signals. The plot shows variations in signal amplitude over a 30-second interval. Two key data points were observed, cursor 1 at negative 0.21 volts and cursor 2 at positive 0.14 volts. By analyzing the time difference of zero point 0.2 seconds, we calculate the frequency as 5.06 Hz, which reflects the periodic nature of the recorded signal. Next, we move to the frequency domain analysis. The frequency plot highlights a dominant peak at 50 Hz with an amplitude of zero point 0.5 volts. This indicates the primary frequency component captured by our microphone. So beyond 50 Hz, the signal strength decreases, pointing to weaker contributions from higher frequency. Okay, to validate the measurements, we employ the logarithmic SPL equation to calculate the decibel values. So using VRMS of 1.14 and a reference voltage, the average dB value was found to be 69.3 dB with a peak of 73.9 dB. The Decilab software and smartphone app showed consistent at 97.7 dB, proving the system's accuracy. So finally, our results highlight the effectiveness of portable microphones for sound analysis. The Decilab software enabled precise processing and visualization in both time and frequency domains. The result also demonstrated MEMS microphones higher sensitivity to frequency variations, making them ideal for application like machine monitoring and environmental noise assessments.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ishaq bin Masidi. My metric number is MA22106. So today I would like to present my part that is a conclusion. Uh, for my part, I will teach you about key finding sound analyzed using Daisy Lab. Sound analysis has a key role in identifying useful sound from noise, especially in industrial or research environment. We use the intensity of the sound in decibels in the study, and we use Daisy Lab software for real-time data acquisition, processing, and visualization. Sound was converted into voltage using a portable microphone sensor and analyzed through FFT, time waveforms, and domain charts to assess RMS voltage, frequency, and decibel levels. However, mobile phone microphone proved to have high fidelity and dynamic range and are cost effective and reliable for such tasks as machine sound analysis. Finally, our work showed that at higher frequencies, MEMS microphones have higher sensitivity due to design features like decreased front chamber size in bottom port design. The result, although with some inconsistency found across identical Kettle units, show the criticality of calibration in sound analysis system. Virtual instrumentation platforms such as DesiLab were found to provide exceptional accuracy and reliability, and proved to have great application in both industrial and research applications. Additionally, this study showed that affordable, high-fidelity microphones such as those available in mobile devices can be used for versatile and effective signal analysis of acoustics.